Hello everyone. Thank you for listening to this presentation. My name is Zawi Xu. I'm a master student, major in software engineering at the University of Electronic Science and Technology of China. The paper I will be presenting today is titled as Variational Information Diffusion for Probabilistic Cascades Prediction. Let me first introduce the content of this presentation. It includes the following 5 parts: the research background and problem statement, which I will give the necessary preliminaries and our problem definitions. And second, I will introduce literature on this field and state our motivations. The third part is our proposed model, Variational Cascade Graph Learning Neural Networks, for short, VCAS. In the experiments we conducted with baselines onto real-world datasets. And finally, the findings and conclusion of our paper. Here's the spotlight of our paper. We studied the information cascade popularity prediction. We proposed a hierarchical cascade learning framework with graph embedding and recurrent neural networks. We studied the uncertainty problem in cascade prediction with variational encoders. Extensive experimental evaluations conducted on real-world datasets demonstrate the effectiveness of our model. Nowadays, more and more content are created and consumed on online platforms. For example, people read news from Twitter, post photos on Instagram, watch videos on YouTube, communicate with other people on Facebook. Various kinds of content have been created on these online platforms, such as microblogs, online news articles, videos and music, events, even for scientific papers. We consider all these contents as information items. Information items can be defined as any measurable entities of information according to the actual demand. For example, the retweet, like count of microblogs, the comment count, views, listen count, participant count, or citation count. This is to say, the information item, in our case, the Twitter tweet, is diffused to a larger audience by through the retweeting mechanism. It's something like, I posted a tweet, and this tweet can be seen by my followers. And one or more of my followers retweeted my tweet, then my tweet can be seen by my followers. When this process performed repeatedly, we call this process as information diffusion in Twitter's social network. So here we define the information cascade as a sequence of adopters of the original information item. For example, all the retweets of a Twitter tweet, or the comments of user of news articles, or citations of scientific paper. Once we have the diffusion path of each participant, that is to say, we know the route how information diffused, a cascade graph can be defined. Take the picture as an example. All nodes are users in a social network. The red nodes are users who retweet the original tweet. The green nodes are users who didn't retweet the original tweet, and the edges indicate user relationships. For example, follower or followee. Given information item, for example, a tweet, by observing the early evolution of this tweet before an observation time, TO, we can observe several early participants. In our case, the retweets. These participants can form an information cascade. If we further have the routine information of the diffusion, then we can get a cascade graph. Just as the figure shows, there are several subgraphs. Each is defined by time step t. The cascade graph reveals how information is diffused in the underlying social network. Consider this tweet was posted by the user A and time t0. Then user B retweet A's tweet and timestamp t1. We call this process as the information or the tweet that user A want to convey to others was diffused to user B. Similarly, user C retweet user A's tweet. We say that the information is diffused from user A to user C and timestamp t2. The information can not only be diffused directly, for example, A to B or A to C, but also indirectly. Take the first subgraph as an example. Say, user D is not a friend of user A, so user D cannot see the tweet of user A. But user D can still retweet user A's retweet by through the user B's retweet, because user B, maybe he's a common friend between user A and D. In this case, we say that user D retweet user A's tweet indirectly. That is to say, the information is diffused from user A to user B and then to user D, and time step T3. Now our problem becomes to this. Given an observed cascade graph G and time step TO, we aim to predict the future retweet count of this tweet at a prediction time TR. I predict how many nodes in cascade graph G and TR. In other words, imagine you posted a tweet, and after a period of time, for instance, an hour, then your tweet maybe has 10 retweets. And now we know this information of your tweet, and we want to know how many retweets this tweet will have after a couple of days. We call this problem state as popularity prediction. Studied popularity prediction has a lot of benefits, both for academia and industry. For example, the viral marketing. We want to know how to promote our products to larger consumers and to obtain the maximum business profits. If we know how information are disseminated among consumers, we could do better to sell our products. For advertisement, similarly, if we know which product will become popular in the future, we can adjust our strategy of advertisement and give more resources to those potential hot products. For recommendation, if we could predict which information item will be popular, we could recommend that item earlier to users. For epidemic prevention, just like the recent coronavirus pandemic, prediction in advance is of paramount importance for both our health and the economy. Another angle, we could even track the coronavirus-related topics in social networks to make prediction. For storage and caching strategy, for example, since videos take a large amount of internet traffic, if we could predict which video will become popular, then we can make strategies such as video resolution optimization or CDN optimization in advance. For scientific impact quantification, we could predict impact of authors, papers, or research topics, which could benefit the funding agencies and research institutes for better policy and decision-making. Existing models on information popularity prediction can be mainly categorized as the following three types: the feature-based models, the generative models, and the recently prevailed deep learning models. Feature-based models mining various handcrafted features from raw cascade data. For example, the temporal, structural, user item, and the content features. The generative models include Poisson process, Hawkins process, epidemic models, and the survival analysis. The deep learning models, for example, the recurrent neural networks, convolutional neural networks, graph neural networks, various kinds of neural networks. Existing models also face following challenges. For example, they often lack an efficient cascade representation learning, which both models the structural and temporal characteristics of information diffusion. And they lack a hierarchical cascade modeling, which both considers the user level and cascade level, and the cascade uncertainty handling is often absent. To address these challenges, we proposed the VCAS model, the Variational Cascade Graph Neural Network Learning Framework, VCAS. It is consisted by the following 4 components: contextualized diffusion embedding, temporal diffusion modeling, diffusion uncertainty modeling, and the predictor. The first part of our model is the input cascade graphs. As shown in the figure, user A is the author of the tweet, and user B, C, D, and E are retweeters before observation time TO. As we mentioned before, given observation time TO, we aim to predict the future popularity of information cascade and time TR. The next step is to process the input cascade graph. We employ a graph embedding technique from graph signal processing to generate node structural embeddings from spectral graph wavelets. The generated node embeddings are structurally equivalent as shown in the right figure. Those nodes who have similar positions in the graph, for example, nodes with the same color in graph, will have similar embeddings. After generating embeddings of nodes in cascade graph, we fed a sequence of node embeddings of cascade into 2 layers of bidirectional gated recurrent units. The learned latent representation H2 can be readily used for prediction. However, when using only the last hidden state of RN for cascade prediction, the model is forced to learn all high-level structures locally on a step-by-step basis, and in a deterministic way. To cope with this problem, we introduce a hierarchical variational encoder to handle the uncertainty and the long-term dependencies in cascades. The proposed deep hierarchical variational autoencoder has 2 components: a subgraph lower level VIE and a cascade higher level VIE. The input of subgraph VIEs are a sequence of cascade subgraphs embeddings. Through an MLP-based encoder, we obtain the mean and the variance, and by using the reparameterization trick, the latent factor Z can be sampled from Gaussian distribution. By minimizing reconstruction error between the input and output, the large latent representation Z1 for all subgraphs captures the cascade data distribution. Once we have learned latent factor Z1 from the lower level VIEs, we employ a higher level cascade VIE to capture the dependencies among participants in cascades. The cascade VIE is based on an RM-based encoder and an RM-based decoder. Through this cascade VIE, we obtain a cascade level latent factor Z2. Finally, we have obtained H2 from the 2-layer bidirectional GRUs and Z2 from the hierarchical variational autoencoders. We concatenate these 2 latent vectors and fed them into a 2-layer multi-layer perceptrons to predict the final popularity P. We conduct experiments on 2 real-world cascade datasets. The first is Sina Weibo, a Twitter-like microblogging service platform in China. The second, APIs dataset, is from American Physical Society. The cascades in Weibo dataset are consisted by tweets and their retweets. The cascades in APIs dataset are consisted by papers and their citation papers. From the right figure, we can see that the cascade size of both datasets follow heavy tail distributions, and typically, popularity of Weibo cascades are larger than APIs, but for structures of cascades, the API's dataset are more viral than Weibo. We compare our proposed model VCAS with several strong baselines, including feature-based, generative-based, and most important, the deep learning-based models. We can see from the chart our proposed model VCAS can significantly reduce the prediction error in terms of MSLE, which is defined as mean square logarithmic error. We also did some other kinds of experiments, including the ablation study, which we analyze the contribution of each component in VCAS model, and the model interpretability, which including counterfactual analysis. We dive into the model to see which cascade we could predict good and which cascade we predict bad. In the latent representation, which we use the TSNE to realize the layered representation, and the parameter sensitivity. If you are interested, you can see details in our paper. Okay, that's all. Thank you for your listening. Hope we could all pull through the hard time because of the coronavirus outbreak. And I wish you and your friends and families the best of health. Goodbye.